So this question says that we have a small disk of radius r1 is mounted coaxially with a large disk of radius 2. The disks are securely fastened to each other and the combined combination is free to rotate about a fixed axis that's perpendicular to the horizontal frictionless surface table that it's on. Okay, that's half the question. The other half says the rotation inertia is a combination of I. Oh, that's cool. They give us the rotational inertia, the moment of inertia of this whole thing. It's I. So we have I. Another string is wrapped around the large disk attached to a block M on the table. Another string is wrapped around a small disk and is pulled with a force F. So we have R1. R1 points in this direction and R2 points in that direction. And we want to know what's the acceleration of the block. Okay, what do we need to do? Well, if I want to know the acceleration of the block, chances are I'm going to need a free body diagram. Free body diagram, I'm looking down on this thing. I'm looking down, so I'm going to say, for sake of this, x, positive x, no, actually, let's be smart about this thing. If I pull F, it's going to spin, this block's going to get pulled forward. So I'm going to do positive x this direction, positive y that direction. So my free body diagram has a tension force on it. So I know that my tension force, tension force is equal to, it's my net force, is equal to the mass of the object times the acceleration of the object. That's great. I need to know what the tension force is to figure out the acceleration. But I want to know this. This is the value that I'm looking for. So this mass is what this acceleration is really what I want. That's great. Unfortunately, we can't get there because we don't know what the tension is. However, we do have a rotational case. So if I have that the net torque is going to be equal to I times alpha. I'm going to be careful with my signs. So if I have x pointing to the left, y pointing up, I'm going to I'm going to keep a right-handed coordinate system and say that my z, positive z, is into the page. Little circle with an x is my designation for into the page. So now when I go through this, I'm going to say, I'm going to look at Newton's second law for rotation, say, hey, what are my torques and how do I get my angular acceleration of this? Well, I know that I have a torque, F, this F right here. F times R1, or actually it's R1 times F, times the sine of the angle between them, which happens to be at 90 degrees, is going to give me my first torque. And I want to get the sine right of this. I want to know what direction does this thing point in. So I do R pointing down, F, I close my fingers towards F, so R points straight down, F points over, and I see that my force, or my torque, R crossed into F, RF, gives a torque out of the page, which is going to be a negative value because it's in the opposite direction of what I said was positive. Positive z's into the page. So in the z direction, I'm in the negative z direction for this one. I have another force. I have a tension force pulling back, right? I have this tension force pulling forward. Newton's third law says that this tension force is going to be what's actually pulling back on this. So for this case, I have R2 times the tension times the sine of this angle. It's 90 degrees. So again, I get another factor of 1 that points out. That should be a 1. So I have R2 times T times 1. And I have to ask myself, is that a positive or a negative? So I look R2 crossed into T, I point into the page, so I add it. And I do one check right here. I see F tries to make this thing spin counterclockwise. T tries to make this thing spin clockwise. So they have to be opposite signs. And this is going to give me I alpha. Well, this is really kind of cool because I see that I have a tension here. So I get, let's see, what do I get? What do I want to solve for? What do I still need? I have F, I have R1, I have R2, I have tension. So let me just clean this up a little bit. I alpha. All right, so what do I get? Well, I see that I have a tension which I could substitute in for. So I'm going to substitute in for my tension. So minus R1F plus R2 times MA, right? This is what my tension is from up here, is equal to I alpha. Let's see, if alpha is into the page, what does that mean? If alpha's into the page, that means it's actually opposite of what my acceleration is. So I'm looking at if this thing starts at rest and starts to speed up, that means this angular acceleration is probably going to be a negative value. So I know that A and alpha, if alpha is positive, or if alpha is negative and it starts to spin up in this direction, that would give me a rotation direction in the negative z direction, then that would mean that A, the string, would be wrapping up on this, and this A would be in the positive direction. So I know that my alpha and my A probably have a minus sign difference. But I look at this equation, oh, and that's actually what I want to do. I need to be able to relate alpha to A. So I know that A is equal to, the magnitude of A is equal to alpha, the magnitude of alpha times the radius. So I'm going to make that substitution in. This is going to be equal to I A over R. And actually there's a minus sign in here just to make sure that my rotations work the right way. So it's a little bit sloppy on my minus signs, but I'm making sure I'm getting it correct here. So this acceleration is at the radius that I'm out. So this is actually R2. So I think I'm going to need some more paper. So go ahead, move some stuff around. I'm going to rewrite this. Minus FR1 plus R2MA is equal to minus IA over R2. Now I want to solve for A, because that's the value that I want. Move this away, slide up, make sure that we can actually see what we're writing. And I get that FR1 R2 with a minus sign plus R2 squared MA is equal to minus IA. I just multiplied through by R2. I'm going to do a plus, and I'm going to change this to a minus sign because that gives me it makes my minus signs work out a little bit better. So I have FR1 R2 is equal to IA plus R2 squared MA. So I get that FR1 R2 is equal to I plus R2 squared M multiplied by A, factoring the value out, FR1 R2 over I plus R2 squared M is equal to A. So I bring back my page over here. I solve for A. I'm looking at R1 R2 F, R1 R2 F, A is not right, over an I plus R2M. So I see value of C is the correct answer. Now I just want to go back and check to make sure that this kind of makes sense to me. So I'm going to look at this equation right here, and see, does this make sense that things are going to change in the right way? If my moment of inertia of my disk gets larger, my angular acceleration gets smaller. This makes sense to me, or my acceleration gets smaller because it's harder for me to move this spinning object. If the radius of R2 increases, this is the one I really want to check. If the radius of R2 increases, that means R2, the torque that I'm going to be pulling that one is going to increase. It's going to be moving at a faster rate, so that's great. Well, let's see. If R2 goes to 0, I'm trying to think of what the cases that I can do. So if R2 goes to 0, that means that this problem, this object becomes smaller and smaller and smaller. At least R2 becomes smaller and smaller and smaller. The moment of inertia, we're going to say, doesn't change in this case, but where we're attaching this string is going to get smaller and smaller and smaller. And this makes sense because as R2 gets smaller, this value goes to 0. This value goes to 0. I'm actually dividing by 0 in the end. If R2 gets larger and larger and larger, the string is going to move at a faster rate, but it's also going to be pulling on me in a different way. So I think this is the right answer. Not too hard of a problem to solve through. We looked at the problem. We said, what is the acceleration of the object? We want to figure out what the rotation is, and then we have to match to make sure that when we substitute in the translation and the rotation equivalence, this A is equal to alpha r, that we make sure we get the right minus sign.